If you ever felt overwhelmed by the vastity of a clear, starry sky, it might not be helpful to realize that all the matter you see and experience, galaxies, gas, our planet, are nothing but less than 5% of the content of the universe. Our cosmos is mostly dark. The structures we live in formed under the gravitational effects due to the dark matter component, and dark energy, accounting for 70% of the universe, is driving the accelerated expansion we are witnessing now. This is what we learned across the last century, building the cosmological standard model, the lambda CDM model, based on Einstein's theory of general relativity. Lambda stands indeed for the dark energy, assumed to be a constant, while CDM refers to the dark matter component. The darkness of the universe might be scary to some, but is actually thrilling for cosmologists trying to shed light upon it. The common approach of research is comparing the theoretical model with data. But which data do tell us about something we cannot directly observe? Cosmologists found out different probes to carry on cosmological investigation from different perspectives, something which is very important to capture all the different processes involved in the evolution of the universe and to exploit their complementarities to draw a clearer picture of the cosmos. Two important observables are related to the very early universe, in particular to the so-called epoch of recombination, when atoms formed for the first time. Before recombination, the universe was filled with a hot, almost universe plasma made of radiation and matter coupled together, and tiny variations in the density field excited sound waves that oscillated through the fluid. After this moment, matter and radiation decoupled, and photons started propagating throughout the universe, producing a signal that still pervades the cosmos, the cosmic microwave background, whose properties carry indeed relevant information about the history of the universe. Another consequence of recombination is that the waves ceased, and the suddenly frozen ripples were left as an everlasting imprint of this event. These wrinkles, known as baryonic acoustic oscillations, can still be observed and used as cosmological probes. Moreover, we can study the large-scale structure of the universe, mapping the three-dimensional distribution of the cosmic web by means of wide cosmological surveys. We can measure the clustering in the universe, for example, looking at where galaxies and gas clump and form denser structures under the effects of gravity. Alternatively, we can exploit the phenomenon of gravitational lensing to recover the matter distribution by observing how it distorts ray lights. Lastly, we can observe standard candles in the local universe. These are objects like supernovae whose absolute luminosity and therefore their distance are known. The Hubble law establishes a linear relation between the distance of a source and its redshift through the Hubble constant h0. If we know the distance and the redshift of a standard candle, it is then possible to infer h0 that measures the expansion rate of the universe at present time. Along the years, we strained our eyes on the cosmos, designing more and more sophisticated experiments, and most of the times, data were in extraordinary agreement with the theoretical expectation. But this is not the whole story. First of all, we still do not know what dark matter and dark energy are. Now we have direct proofs about what happened in the very first seconds of life of the universe. And there is an even more subtle issue. In some cases, we get different answers depending on the probe we are interrogating. In the last years, some tensions between datasets emerged, and they keep getting stronger as new data are available. The Hubble tension is the most striking example. The late universe and the early universe point toward two different and incompatible values of the Hubble constant h0. Measurements of the Hubble constant made with a sample of supernovae, but also using other standard candles, provide a value which is higher than 70 km per second per megaparsec. On the other side, the analysis of the CMB favors a lower value, and the discrepancy now reached the level of 5 sigma. Another tension is related to the abundance of matter in the universe and on its clumpiness, that are parameterized with a S8 parameter. In this case, the CMB is in disagreement with what we infer from surveys of the cosmic web, indicating a higher value of the S8 parameter. Where do these tensions come from? And how can we solve them? Well, there are two possible solutions. The first one is the presence of systematics in our data, something we are missing in our analysis which could be responsible of the disagreement between probes. The other possibility, which is very intriguing, is that new physics is hiding behind these tensions. This scenario opens a wide landscape of theoretical investigations concerning the validity of general relativity on cosmological scales, models of dark energy more complex than a cosmological constant, or the existence of new species or interactions between the ones we know. Dealing with new physics is of course compelling, and cosmology is not the only field that seems to need a theory beyond the standard one. Extension of the standard model of particle physics are required as well. But it's not easy to build a consistent theory that is also able to reproduce all the observables we already probed. And moreover, at the moment, none of the proposed models can solve both the Hubble and the SA tensions. Typically, when one of the two is alleviated, the other one gets even worse. If we want to find the resolution of these questions, we then need to be in control of all the possible systematics in the data, and at the same time pursue the investigation of new models and on how to test them. And since the answer is there in the universe, observations and new probes are essential. In the next years, many new cosmological surveys will scrutinize the cosmos with unprecedented accuracies. And now we are also able to hear gravitational waves. So it's really up to us to be always curious and willing to learn more and more by keeping our eyes, ears, and minds open toward the universe.